Well, the last year as well as this semester, all the quantum mechanics that you have learned, uh, that concerns a single particle. A single particle in whatever potential it finds itself in, a single particle with a spin, a single particle. So all that had concerned a single particle. But in physical reality, we never come across a single particle isolated from the rest of the universe. So we need to consider what happens if multiple particles are put together, what kind of behavior they exhibit. That subject is quite expectedly a bit complicated. So we will take step-by-step approach to develop the understanding. And naturally, the first thing that we can do is to consider two particles. So there are two particles. Now, whenever you see two tennis balls, these tennis balls might look identical, might look the same. And when you play with a tennis ball and somebody supplies with the other tennis ball, you sometimes may not be able to distinguish which is which. But actually, if you look minutely, you would know that this is ball number 1 and this is ball number 2. In nature, when we deal with minute particles, electrons, photons, protons, and things like that, this distinguishability is erased. That means you cannot really make out whether it is this electron or that electron. In order to understand the character of that kind of a particle, and there are also particles which can be distinguished. So we need to take step by step. First, we'll consider two distinguishable particles. So first, we consider two distinguishable particles. These two distinguishable particles, that means you know which is which, find themselves in some potential function. You might consider that they are in two different potential functions that really won't matter. And then we will be able to write the Hamiltonian function as h is equal to p square by twice m, but p1 square by twice m for the first particle. I'll say to n1 plus p2 square by twice n2 for the second particle. And if they find themselves in two different potential functions, p1 x1 plus p2 x2. For our purpose, it will not really make much of a difference if we consider them to be in the same potential. That means two particles released in a, say, harmonic oscillator potential or something like that. So for the rest of it, we will consider the same potential function. So let's not put V1 and V2. But all I'm saying is that if we consider V1 and V2, still the same thing will apply. So there are this one potential function, but this the force experienced by the first particle will be dependent on the position of the first particle. The force experienced by the second particle will be dependent on the position of the second particle, and therefore these have to be written in terms of x1 and x2. And the way we convert the Hamiltonian function to a Hamiltonian operator is by converting these into their equivalent operator forms, right? So our P1 will be written as minus I h cross del x1. P2 operator will be written as minus I h cross del x2. These are important. And therefore, this can be then cast in terms of the operator form as minus h cross square by twice m1 uh, del 2 del x1 minus h cross square twice m2 del 2 del x2 plus the same things v x1 plus v x2. Okay? And then in that situation, we will not write the psi function of this particle and that particle separately. There will be a psi function that is dependent on x1, x2, and t. Okay, so the psi function is psi is then x1, x2. Then we will be able to write the Schrödinger equation in terms of this psi function. That means this is now a whenever we consider a system comprising two particles, three particles, there will be a wave function which is dependent on all these particles, but there will be a total wave function. And in terms of that total wave function, the Schrödinger equation will take the form I h cross del del t of psi x1 x2 t that should be equal to the Hamiltonian operator, this operating on psi x1 x2. By the way, here I have to mention one thing, that in defining the potential experienced by the two particles, we are assuming that they do not interact with each other. Had they interacted, there would have been another term, something like x1 minus x2, and this we are not considering. Presently, we are considering non-interacting particles. We will later consider interaction, but presently let us, as I said, develop the material step by step. And so first let us consider non-interacting particles, and then only you can write in this form, otherwise you will not be able to. So if you have written the Schrödinger equation in that form, then you can, the way we have always solved Schrödinger equations was to separate out the space-dependent part and the time-dependent part, and assume this is something that you have done in solving the infinite square wave potential, in solving the harmonic oscillator case and all that. All the time we have assumed that, so we assume the psi x1 x2 t can be written as x1 x2, and there is another function, say t, a product. Now this is something that runs through physicists' treatment of partial differential equations. We always assume first that it can be written in a product form of two separate variables, and then we check whether that works or not. This is not typically the way a mathematician deals with the problem, but a physicist always tries this out, and if it works, then that is the best possible solution for us. If it does not work, then we have to look for some coupled solution. So in this case also, we will try to work out by assuming that a solution can be found of this form. Uh, so this will have two parts. Then, if you substitute it in the Schrodinger equation, then it will be found to have two parts. It can be broken. It can separate it out in two parts. The first part, as you know, it goes exactly the same way as you have done in the last semester. So I'm not repeating each step. The first part will come out to be, I'll write here so that I have that space. T of t will come out to be e to the power minus I, sorry, et. Et by h. So this is something that always happens. So this is uh, the time dependent part, and the space dependent part takes the form, the time independent part. So this is the time dependent part. And the time independent part takes the form, let me write it, minus, it was minus h cross square twice m1 del 2 del x1 2 minus h cross square twice m2 del 2 del x2 square plus vx1 plus vx2. This whole thing will apply on psi x1 comma x2, this part. Then this will be equal to the energy eigenvalue times all right. So this is the time independent part, and again we look for solutions of the form. Well, this is also a partial differential equation because it depends on two variables, x1 and x2. And the way I said that the technique runs through physics, we will again assume that it can be broken up into a product form, one part dependent on x1, another part dependent on x2. So we assume, let me again give some space. Assume that it can be written in this form, psi x1, x2 can be written in the form psi n x1 and psi k. So the subscripts indicate that these are the energy eigenfunctions of the independent particles, each of these, and we are assuming that the total energy eigenfunction can be written as a product of the individual ones. This, we are taking that liberty. This is possible if we are considering non-interacting particles, and we will see that this is actually possible. So now, I need space. Okay, let me delete the top part. Yeah, this is something that will work out here. So just remember that this is coming here. Then we substitute. In place of psi x1, x2, we substitute this. So as a result, we get minus h cross square by twice m1 del 2 del x1 minus h cross square by twice m2 del 2 del x1 x2 plus v x1 plus v x2, whole thing applied on psi n x1 psi k x2, and uh, that will be equal to the energy eigenvalue times psi n x1 psi k x2. Okay. Uh, at this stage, let us make our life a little more simpler. If we assume that there are two electrons in the potential well, then these two m's are the same. So let us it will make our algebra a bit simpler. So let's assume that both have the same mass. Okay. That will not, that's without loss of generality. If you had assumed m1 and m2, it will not really matter. Now, uh, notice that the operator related to x1 does not affect this term, and the operator related to x2 does not affect this term. Similarly with this, right? So it is then possible to sort of separate out. So if I now operate this on this, this term will first remain unchanged, and this operator will operate only on this. So we can write uh, psi k x2 psi k x2, and then it will be the operator corresponding to the first particle. They are distinguishable, so we can identify these as m del 2 del x1 2. I'll only take the operator corresponding to the first one, and this operates on psi n x1. Similarly, I'll now need a little more space, so I'll delete this part.
So,
Yes.
excuse me, sir. Sir, in that, assuming that phi of x1 x2 is equal to phi n x1 and phi k x2, isn't it? Isn't that directly follow from the thing that it is non-interacting? Why do we need to assume that?
Well, if you think that that follows from common sense, you are at a higher stage than I am. I would like to prove that it really works. Okay. So it is, yes, if it actually follows from the fact that they are non-interacting, that's true. But see, I have not only divided that into two parts, psi x1 and psi x2. I have additionally says that these are the individual energy eigenfunctions, the nth energy eigenfunction and the kth energy eigenfunction. So this is a slightly stronger statement I have made, and therefore I need to prove that it really works. That's what I'm doing, nothing more. Okay, and if it follows from common sense, then I'm also happy with it.
Thank you, sir.
Okay, now let us operate on the second one. You will get plus, uh, it will be then psi n will come out, x1 will come out, and the second particle's operator will operate on the second particle. That operates on the second particle. It is okay. And this is our E. Okay, now here we have a situation where we have written it in this form, and now we can just manipulate it by dividing it by this term. Okay, dividing through by this term. So this will give 1 by psi n x1, because these two were there and I have divided, so this will be there, and then the rest will remain minus h cross square by twice m del 2 del x1 square plus b x1 operating on uh, psi n x1 plus 1 by psi k x2, and this term remains the same. Okay, I'm not writing again. Is equal to your e. Okay, is this part. Now you see that this part is entirely dependent on x1, and this part is entirely dependent on x2, and they sum up to give a total energy. And therefore, it stands to reason that this part represents the energy of the first particle, energy eigenvalue of the first particle, and this one represents the energy eigenvalue of the second particle. So it stands to reason to think that way, and therefore we can possibly write this as E1, or it was nth eigenstate, so it's better to write n plus e k is equal to total. Okay, which means I'll erase this. Which means that individually we can write each part as uh, 1 by, sorry, this one, 1 by psi n x1 minus h cross square by twice m del 2 del x1 2 plus b x1 psi n x1 is equal to e n, and I can bring this one here, so I'll just delete here from here and multiply it there. It immediately is clear that for the first particle's corresponding operator operating on this, you get En this, which means that this is the first particle's nth energy eigenvalue. This is the eigenvalue equation. Clear? And similarly for the second particle. So similarly, I'm not write it. So similarly for the second particle, you will get another equation. So this times psi k x2 is equal to ek psi k. So it is immediately clear that these are the energy eigenvalues. So we have been able to establish that the psi as a function of x1, x2, when we are talking about the energy eigenvalues, eigenvectors, eigenfunctions of the time independent Schrodinger equation, then we can write it as a product of the individual energy eigenfunction of the two particles. That's what we have just established. Well, at this stage, it will be good to have an idea what this psi x1, x2 actually mean. Let me delete this. Because the physical interpretation is important, that idea must be clear. What does psi x1, x2, or maybe also with t if you consider the time dependent part, what does it mean physically? We know what the psi function of an individual particle means, that we know, Born's rule, right? In this case, what does Born rule say? let me write what the bonds will say, because it might be better for you to write it down. In this case, the bonds will say the probability of finding particle 1 particle 1 uh, in a small neighborhood or interval, small neighborhood, delta x centered on x, uh, and now this time we have to consider the other one also, and particle 2 in a small interval this is x1 centered on x1 interval delta x uh, 2 centered on this is what is given by the Bonds rule, and this is now mod psi x1 x2 e mod psi square uh, del x1 del x2. So Bonds rule says that the particle exists in a space something like this, which two coordinates x1 and x2, x1 and x2. The probability of we finding it in a box like this is given by this. Okay, in a box in the phase space is given by this. And since the particle has to be somewhere in this space, therefore the normalization rule should be that integral minus infinity to infinity, integral minus double integral minus infinity to infinity, because x1 and x2 we have to integrate over both, and it is psi x1 comma x2 comma t square del x1 del x2, that should be equal to 1. That's a constant that you have to impose, because the particle has to be somewhere. And you might also be interested in finding the probability of finding the particle 1 independent, no matter where the particle 2 is. That's another kind of question that we might ask. Where is particle 1 in this two particle system? And I don't care where the particle 2 is. So that that will be given by the probability of finding the particle. I'll not write the whole thing. Probability of finding the particle at x1. Okay, in a range delta x1 centered around x1. In delta x1, sorry, delta I was writing that. Delta x1 around x1. This will be equal to, it is 1 integral minus infinity to infinity. It will be psi x1 comma x2 comma t mod square. I have to integrate over all delta x2s. Okay, this whole thing in a bracket delta x1. So it's also possible then to find where the particle is, a probability distribution of only the particle 1, no matter where the particle 2 is. So that's given by this. So this is the another expression of the Bohn's rule. So the Bohn's rule sort of conceptually remains the same. Only thing is that you have to take into account the fact that we are now talking about two particles, not one. Yeah. Great. Now, in this situation, we when we have found that the two particles, their wave functions are for all practical purposes sort of decoupled. They can be thought to be independent of each other. Then we can write the Bohn's rule in this form in this particular case as psi uh, x1 x2 mod square uh, delta x1 delta x2. This can be written as uh, mod psi n x1 mod square. It will be 1 over delta x1 times mod psi k x2 square delta x2. Okay, so we can, for all practical purposes, separate them out and talk in terms of their own individual eigenfunctions, and let us see what the implications of that are. We will draw a space like this and draw the probability distributions, the two particle probability distributions. Okay, so for that I'll get some space. So what we are trying to do is that okay, we have to think of some particular v function. Let's consider something that is simpler enough, uh, the infinite square well. Okay, in the infinite square well, we know that the first two uh, eigenfunctions are like this. Okay, now assume that two particles are in a infinite square well. One of them is in the ground state, so this one we assume to be 0, and this can be assumed to be 1. The second one is the first excited state. How will it look? How will the probability distribution look in the phase space? Let's try to work it out. For better lines. I got two pictures. First, I will assume that this one x1, the first particle is here is my x1 x2 space. Here is my x1 x2 space. I'll first consider the first particle is in the ground state. So first particles eigenfunction will be like this, and second particle's eigenfunction will be like this. Now, how do we draw that probability distribution in the phase space? It will be like a contour plot. The same probabilities are drawn with a line, and then it will have one like this, another like that, another contour like this, another contour like that, and so on and so forth. Let's tend to reason. So the contour plot, effectively, if you on your computer draw it by the modern plotting techniques, then this will be higher color. They look like two humps, two mountains. Okay, arranged in this particular way. And now, if you instead consider the second particle in a ground state and the first particle in the first excited state, then you will have a picture like this. the probability distributions will be like this. Now, what I'm trying to drive at is that these two are different pictures. Different pictures because particle 1 and particle 2 are distinguishable. You can distinguish which is which. And so you know that the particle 1 is in this state, particle 2 is in that state. And when we go into indistinguishable particle, we will not be able to make out. We only know that one is in ground state, another is in first exercise state, and the whole picture will change. So the first I wanted to give an idea what happens for a distinguishable particle case. It is this that happens. Okay, is that clear? Okay, so let us break for some time to take questions, and then
Excuse me.
yeah.
Can you reiterate this point? How did you plot these contours?
The contours were that this particle has a larger probability of being here,
These
right? And this particle has a larger probability of being here and here, right? So there is a higher probability of the combination to be in here and in here, right?
right, sir.
And
Yes.
if we then plot the equal probability lines, these are the contours, equal probability lines. This is the maximum probability point. This is the maximum probability point. The combination is maximally likely to be in either of these 2 points. Is it clear now?
Yes, sir.
How we are plotting it? Yes. Any other
And sir,
question?
there's one more.
Yeah.
Yes, sir.
Yeah.
In the notation, when you assume two different particles,
Yes.
you assume them to be in psi n and psi k state. What do these n and k represent here?
These are actually, you see, if you consider the uh, the uh, the infinite square well, then the particles can be in their distinct eigenfunctions. Ground state is psi 0, the first excited state is psi 1, and so on and so forth, right? So each eigenstate is marked by a number 0, 1, 2, 3, 4, and that is what the n and k are. So
Sir,
these,
actually, I have a doubt in.
these actually represent the energy eigen functions of particle 1 and particle 2. Nth eigenfunction here, kth eigenfunction there. Yeah. What is the question, Bill?
Yeah, sir. So particle 1 and 2 can be in the superposition of their eigenstates, right? So it is need not be that we are like we can say surely that the particle 1 is in psi n state. It can be in a linear superposition of all its eigenstates, and similarly for particle 2.
Right. Yes. Sure. Each of these can be in a linear superposition of these. We are assuming, presently we are assuming that the psi 1 is in a particular eigenstate, psi 2 is another particular eigenstate. That means particle 1 is in an eigenstate, particle 2 is an eigenstate. It is true that particle 1 could be in a linear superposition of its own eigenstates. Particle 2 can be its own linear superposition its own eigenstates, but we are sort of assuming that each one is in a stationary state. If they're in combination, they are not stationary, right? If they're in combination, then they have their own individual phase factors, and as a result, the wave function will not remain stationary. Now here we are imagining such a way that the individual wave functions are stationary. Then it will work. Otherwise, what will happen is that these will all start dancing and oscillating. Okay, we are starting from the simplest case first. You are right that these individually they could be in a linear superposition of the possibilities.
And sir, the thing which you said now, stationary. So like no, I don't get this point. Like how can like even for a single wave function, how can that it be stationary? We know that it evolves with time. So like can you describe what is stationary and what is not stationary.
Oh, a stationary state is something that does not evolve with time. So
So,
if you
but
have
there,
if you have a single particle and its wave function is actually its eigenfunction times the phase factor, then if you do a mod psi square, the phase factor disappears,
oh,
and what
okay, okay,
remains
sir. Yes,
remains the same,
yes, yes.
independent of time. So it does not evolve with time.
Got it, sir. Got it.
So a stationary state is where it does not evolve with time, and we have shown that it is possible to express the collective wave function of the two particles in terms of the individual stationary states. That's all.
Got it, sir. Thank you.
Continue with uh, with a with a with the point that the particle, an electron, for example, if two electrons are released in a particular potential well, they also have spins, right? How do we put the spin? How do we consider the spin along with the spatial distribution of probabilities, along with the spatial psi function? Now, this is in this part, I will use a particular notation. So let me introduce the notation first, because in books you will find different books, you will find different notations, and so what I will do, let me explain. So uh, the spin up state we have already denoted as, but we have said that this can be psi a, up x, up y, up z, and all that. Now, in this particular part, when we do the exposition, we could have taken up x, up y, up z, and all that, but uh, the the x, y, and z depends on in which direction we have oriented our analyzing equipment, like the Steingart-like apparatus. And in this case, we will assume that it is oriented in the z direction. Therefore, whenever we say up, it actually means up z. Okay. So this is one convention that we'll take, because otherwise every time we'll have to write a subscript, it will be cluttering of notations. So similarly, spin down will be, when I write this, it will essentially mean that it is down. Okay. Oh, I should have put it inside. Yeah. In books, you will find that for an electron to specify the spin state, you'll need to specify the value of s. S for a electron is half, and the spin magnetic quantum number, which is plus minus half. So uh, there are books in which the state is written in this form: s is equal to half, comma, ms is equal to plus half or minus half, something like this. And I find this notation a bit cluttered, because the whole thing can simply be written as, that's it. So I will take this notation, but you have to remember that in books you will find this kind of a notation. It is same as what I'm writing as just now. And our convention in this chapter will be that our magnetic field is oriented in the up direction, or in the z direction. Therefore, when I say up, it is always up z, not up x or up y. And in this case, you also have to remember that our s square is s plus 1, s plus 1, h cross square is s plus 1. You put s is equal to half, it gives always 3h cross square. So that is always true, that the s square, that operator's eigenvalue is always 3h cross 5. That's something we have to. So is the abbreviated notation clear? So let us go ahead with that abbreviated notation. I will use this notation. So you need to know what it means, and sometimes you may find it at odds with the way some books give their notations. Some books give this way, and right. So these are essentially the same as this one is up, this one is down. I would strongly recommend you to read books also. Huh? If you read books, for example, book by Sakurai, the book by Kohen Tanuji, the book by Shankar, uh, then you will see how they treat a subject. Everybody has a different way of treating a subject. I also have a different way of treating a subject, and how I am going step by step in introducing various concepts, which will differ from the way some books introduce some concepts. Every teacher has a way of understanding and making others understand. So this is my understanding. So it is then clear with my notation that S1 square, S1 is the first particles. I'm not the subscript one implies that I'm now talking about the first particle. Uh, when that operates on the up state of the first particle, then that is, since it is the up state, it will give P by 4 H cross. Okay, that's the eigenvalue. If you apply SZ operator operating on the up state of 1, uh, then you will get, since it is up, it is plus half. So this is then the eigen vector of this operator and with this eigenvalue. This is the eigenvector of this operator with this eigenvalue, and so similarly for what 2. So for 2 also you can write similar eigenvalue equations. So the point is that if they are distinguishable particle, you know which particle is in up state, which particle is in down state. Suppose one is up, 2 is down, then we can write the combined spin state. The combined spin state can be written as say first one is up, second one is down, and so on and so forth. Okay. Or in some books you will find that some books write it this way. This one is 1 and 2. Some books write this way, but we will use this particular notation. Okay. And it is also possible to abbreviate it even further if we, after all, the whole purpose of the direct notation is that if I can convey what I mean to you, and you understand the same thing, then I can use anything inside the kit. So I can also say, now here there is a positional convention. The first one is always related to the first particle, and the second one is always related to the second particle. So there is a positional convention here. This immediately means that this state is not the same as this state. Okay, because in this case I assume that the first particle is up, second particle is down. In this case, first particle is down, second particle is up. They are not the same. Distinguishable particles, right? So they are not exactly the same. So now, what will be the result of operation of this kind of an operator on the joint spin state? The advantage is that the operator related to the first particle does nothing to the second particle, and the operator related to the second particle does nothing to the first particle. So if I apply SZ1 operator on the, I'll write it this way so that it is easier for you to understand. It may take some time to get used to this kind of a notation. So, and then I can write that this is only operating on this. So SZ1 operating only on up 1, and then the down fellow remains unaltered. And this is nothing but, we have already seen, this is plus half H cross. Uh, this is up 1, and then this remains unaltered. So this operating on the combined state gives just this as the eigenvalue. Okay, and similarly for the second particle. I'm not writing each equation for the two particles. Uh, okay, let me just write once. SZ2, there's another reason for which I need to write. It is up 1, down 2 is equal to, it will be minus half H cross, sorry, up 1, down 2. Now you might add these two equations so that you get a combined operator SZ1 plus SZ2, the combined operator operating on, now I can use the shorter notation, and since these two cancel off, is equal to 0, which means this is the operator for the total Z component. Of spin. Now this comes to 0 because one particle is up, another particle is down. They ultimately the total spin obviously is 0. Now I've got 5 minutes. Just let me introduce a concept. Let me delete this. Now we need to put all the spin stuff along with the spatial wave function stuff, right? There was a spatial wave function which was psi x1, x2, t. And there is also a spin that we have now introduced. What will be the combined state, including in the two particle state, including the spatial wave function as well as the spin state? Now that again has the advantage. What do you do ultimately with such state? You operate on Bison operator. Now the way the operator for the first particle does nothing with the second particle, similarly the operator for the spatial wave function, for example the Hamiltonian operator, does nothing with the spin, and the spin operators does nothing with the spatial part. Because of this, we can get away with a very simple way of representing the combined state. Combined means the spatial as well as the spin state, simply by writing it as a in some books you will find it is written like this: ms1, ms2. In our notation, it is just up down. Okay, so we can write it like that. So let me also write in our notation. I'm often writing the book's notation because this is something you will find in books. So we can simply write it like this, because when a Hamiltonian operator, spatial Hamiltonian operator, operates on it, it leaves this alone and it only changes this part. When a spin operator like the S square operates on this whole thing, it leaves this alone and operates only on this, and that too depending on which spin spin, which particle spin operator we are considering, it will either work on this or on this. So we can write like this, and since we are considering only stationary states, so for stationary states, we can write it as psi 1, 2. This is the notation for the joint stationary wave function. that can be written as psi x1 comma x2 the way we have written earlier, and then the state, or I would rather like the general form right now, and then we'll write it, because here we are specifying the first one is up, second one is down. So ms1 ms2, the general form. This can be up, this can be down, this can be down, this can be up, but we can write it in this form. And then, since this can be separated out into the two parts, so we can write psi n x1, psi k x2, and then depending on which particle is in which state, we can write something like this. So that when the spatial Hamiltonian operator, this is spatial, the spin also has Hamiltonian operator, spatial Hamiltonian operator operates on this, then what does it do? It operates only on this. So Hamiltonian operator operates only on the psi n x1, psi k x2, up 1, down 2, and then it only operates on this, and we have seen that this leads to En plus Ek comes out, psi n x1, psi k x2. Again, this remains unaltered. Okay, so it means that this is something like E psi. So the Hamiltonian operating on the total, it's not a wave function, for a state, I would say, because wave function is only this part, this is the spin part, ultimately the total state. Operating on this gives the energy as eigenvalue. Similarly, if you operate it, oh, sorry, it's time. Okay, I'll just stop here. But you can easily see that if you operate it on S Z1 on psi 1, 2, then this will remain unaltered. This will only be affected, and ultimately you will get plus half h cross psi 1. So this then is the eigenfunction of both the spatial Hamiltonian operator as well as the spin operator, and everything comes out nicely as the eigenvalue. So we can then represent the total state in this kind of a form. Okay, that's what I wanted to make. So let's stop. We are already past my time.